For this RFQ I received from the customer 1 3D part CAD file, 2-dimensional drawing, 3 requirement for validation 13 pages all written in the German language, 4 estimated annual volume, 5 no timelines or a due date for the first shipment. My job for this request for quotation is to advise for manufacturing feasibility, manufacturing process, and tooling. The molded part in this video looks easy, however, the requirements on the drawing makes the manufacturing process very difficult. It can generate high tooling maintenance, too much scrap, and a very costly quality issues. For this presentation I will not go very deep in tooling issues and the validation plan, because the part geometry is basic. However, when I took a quick glance on the 2D drawing I noticed requirements for precision manufacturing processes. Injection molding and CNC machining are required for this job. The plastic resin is 30% glass filled with the precision dimensional tolerances for the molded part and the machined surfaces. When I analyze the customer request for quote, I look for and provide the followings: 1 draft angles, 2 shut-off angles, 3 wall thickness, 4 uniform wall thickness, 5 radii at all corners, 6 plastic resin and the kind of filling, fiber reinforced, heat stabilized, metal filling, 7 the part environment in the final assembly, engine, gas tank, interior exterior etc. 8 safety risk, for example parts that goes in the gas tank, are high safety risk and the manufacturing environment must be free of dust and flash. 9 requirement for validation and cleanness. 10 tonnage or the required clamp force. 11 cycle time. 12 estimated annual volume. 13 cavitation. 14 downtime. 15 backup tooling. 16 production hours. 17 number of tools. 18 efficiency. 19 repeatability. 20 manpower. 21 floor space in the plant. 22 dimensional requirements, GD&T tolerances and datums. 23 manufacturing process. 24 assembly process, press fit, snap fit, ultrasonic welding, inserts adhesive and bond, crush ribs etc. 25 molded part weight. 26 approximated cold runner weight. 27 scrap rate and regrind usage. 28 guesstimated warpage, flow, and uniformity. 29 moisturized packaging. 30 living hinges. 31 packaging. 32 gauges and go-no-go tools. 33 assembly tools and fixture. 34 molded in color, colorant, painted surfaces and paint grooves. 35 plated surfaces. 36 texture and surface finish. 37 weld lines. 38 slides and lifter angles. 39 exchangeable tooling inserts. 40 undercut features, core pull and slides lifters. 41 manufacturing process single shot or 2 shot and material bond and peeling. 42 warranty. 43 best practices. 44 special characteristics. 45 high-risk molded part details and critical notes. 46 molded part features ribs bosses, molded threads. 47 part details that can create thin steel conditions in the mold. 48 plan for prototypes. 49 design for manufacturability and assembly, insert molding, mechanical interlocks. 50 service and maintenance. 51 validation plan. Load, force, environment, and special validation and validation levels in the assembly. 52 filling system and gates. 53 specified tests, methods, equipment, and acceptance criteria and must be clearly defined and understood. 54 have special characteristics been selected? 55 is bill of material complete? 56 are reference dimensions identified to minimize inspection layout time? 57 can existing and available inspection technology measure all the dimensional requirements? 58 material handling and storage. 59 mistake proofing pokayok. 60 capacity. Does the available manufacturing equipment have enough capacity to handle forecasted production and service volumes? 61 new equipment. 62 new tooling. 63 new test equipment. 64 preventative maintenance and spare parts for tools. 65 customer statement of understanding for part design and manufacturing. 66 who is design responsible? 67 is the part design 3D and 2D data finalized and released for tooling? 68 do we have to provide design services and support? 69 tuned molded part geometry. 70 timelines. 71 start of production. 72 manufacturing plants. 73 tooling cost. 74 plastic resin and components costs. 75 ejector pin locations and marks. 76 parting line sharp edges. 77 gate vestige. 78 capability. 79 the industry commercial tolerances. 80 precision tolerances. 81 the plastic resin manufacturer recommendation and mold flow analysis. 82 reverse engineering or Kentucky windage. 83 does the customer accept design concessions to permit normal tool action and standards? Which will be determined during the initial mold design. 84 capital investment. This is the part dimensional requirements. I will review every note section and views. Now we will look at this section. I have added the red arrows for you can see the requirements for the secondary manufacturing process for the molded part. The secondary process is CNC machining with a call out for surface roughness. Also in this section view the arrows are pointing out a very small groove that requires ongoing data collection for concentricity. The groove is in a counterbore hard to measure. Concentricity is considered one of the most difficult GD&T symbols to measure due to its difficulty in establishing the midpoints of the feature. First you must establish a datum axis which to measure. Once the datum axis is established you must now take measure many a series of cross sections, however many is realistic. Once the cross sections are taken and the exact plot of the surface is obtained, the median points of these cross sections must be determined. Then these series of points must be plotted to see if they fall within the cylindrical tolerance zone. This can only be done on a CMM or other computer measurement device and is quite time consuming. As you can see in this picture the arrows are pointing out additional requirements for ongoing data collection for concentricity. The tolerance for this is a precision tolerance and it does not count for the molding and the machine stack tolerances. This is a molded part with a dimensional requirement for a part made of steel with a machine tolerance. Concentricity when used, for your info. Due to its complex nature, concentricity is usually reserved for parts that require a high degree of precision to function properly. For example, transmission gears, which need to always be coaxial to avoid oscillations and wear, may require concentricity to ensure all the axes line up correctly. Equal mass or inertial concerns are one of the leading causes for the concentricity callout. Any application where the median points of a feature need to be controlled relative to a datum would require cylindricity. However, in many cases, the use of runout or true position can replace the need for concentricity and be much easier to measure for. The customer is allowing a parting line, offset and no flash for a machine surface. Interesting, I will let this one go, no comment. Packaging. I could not find in the RFQ any information for the required packaging. Also this part is made of nylon. I would like to know if the customer want us to ship moisturized parts in a sealed plastic bags. The drawing has these specifications for reference, however, the customers did not provide the specifications documents. I must have the specification documents. These are the general notes I found on the drawing. The customer is concerned about the gate location. For this reason we must ask for his approval for the gate location during the mold design. Validation plan. The required validation plan is written in the German language. I could not translate it to English. I need the English version of this validation plan, otherwise I can't quote the project. Part weight and tooling. Material PA610, 30% glass filled. Density 1.31 grams cubic centimeter. Part weight 6.5 grams. For the cold runner, add 2.5 grams for each part cavity. Total weight equals 6.5 plus 2.5 equals 9 grams. Shot weight. Option number 1, if we build an 8 cavity mold, the shot weight equals 8 parts plus 4 runners equals 72 grams. Option number 2, if we build a mold 4 cavity, the shot weight equals 4 parts plus 2 runners equals 36 grams. Manufacturing process: injection molding and CNC machining. This calculation is for a 4 cavity mold with 2 hot drops to cold runner to tunnel gate. Press tonnage equals 130 ton. We will build this tool equivalent to SPI class 102. The estimated mold life is not to exceed 1 million shots. The customer must pay for the tool major maintenance. Major maintenance is half the anticipated lifetime volume, however, the volume can't be more than 1 million shots. For this tool we will have to plan for major maintenance every 300,000 shot because the material is 30% glass nylon. These are calculated data for the injection molding only. Estimated annual volume 360,600 parts. Defect rate 5%. Part per cycle 4 parts. Cycle time 42 second. I know I can mold parts in less time, but I used 42 second for safety. Operator efficiency 85%. Number of machines 1. Run hours per day 8. Run quantity 378,630. Run time hour 1104.34. Downtime hour 165.65. Production time hour 1269.99. Production time days 162.20. Production rate parts per hour 298. Manufacturing process: injection molding and CNC machining. This calculation is for 8 cavity mold with 4 hot drops to cold runner to tunnel gate. Press tonnage equals 200 ton. We will build this tool equivalent to SPI class 102. The estimated mold life is not to exceed 1 million shots. The customer must pay for the tool major maintenance. Major maintenance is half the anticipated lifetime volume, however, the volume can't be more than 1 million shots. For this tool we will have to plan for major maintenance every 300,000 shot because the material is 30% glass nylon. These are calculated data for the injection molding only. Estimated annual volume 360,600 parts. Defect rate 5%. Part per cycle 8 parts. Cycle time 42 second. I know I can mold parts in less time, but I used 42 second for safety. Operator efficiency 85%. Number of machines 1. Run hours per day 8. Run quantity 378,630. Run time hour 552.17. Downtime hour 82.83. Production time hour 634.99. Production time days 81.10. Production rate parts per hour 596. This page is for your info only. Mold maintenance as defined in the industry. Major maintenance: half the anticipated lifetime volume, but the volume can't be more than 1 million shots. For major maintenance, the customer should be involved because he will have to send his tool engineer for the mold evaluation and define the required work for the mold. The customer should pay for mold components worn from production or bad part design. Supplier should pay for mold damage from lack of maintenance or careless use. Usually these kind of details requires a meeting, and the cost for the major maintenance is split accordingly. Inspection: every 20,000 cycles, or every 10 days of production. Maintenance: every 100,000 cycles, or every 10 production runs. Required gauges and fixtures for this job: 1 go-no-go gauges and a CMM holding fixture for measuring concentricity. 2 holding fixture for the CNC machine. Note, we will have to outsource the machining process to a local supplier, because we don't have the CNC machine for this project. Note, our machines and process in our plants are not for precision injection molding, they are designed for commercial manufacturing, with reasonable tolerances for the specified plastic resin. Regarding tolerances shown on this drawing, they are precision tolerances. If we take on this project, the customer must change the precision tolerances to commercial tolerance, for PA610 30% glass filled, and we must use recommendations from the plastic resin manufacturer, with references to results from the mold flow analysis. Our quotation does not include adding Kentucky windage or reverse engineering to any of the part geometry. However, we will design the mold to minimize warpage and ensure holes locations and size are within the required specification. As we all know, mold design, gates position, and process control can only minimize warpage. However, the plastic material behavior cannot be corrected 100%. Therefore, a practical tolerance must be negotiated. Design concessions may be required to permit normal tool action and standards, which will be determined during initial mold design. Examples: add more draft for shut-off surfaces. Add draft to die-locked walls. Lifters angles can't be more than 12 degrees. Slides horn pin cannot be more than 20 degrees. We will try to eliminate thin steel conditions with the recommended design changes to the part 3D data. We will make sure lifter's bath is clear and has enough travel for the required molded geometry. The industry standards for shut-off surfaces and parting lines can't include a radius, because we must maintain good tooling conditions, be steel safe, and minimize downtime for maintenance. The required draft and shut-off angles must be added to the part geometry. Split parting line will leave a visible witness line. The parting lines will be sharp. These are noticeable manufacturing requirements the customer must accept and approve. Hot runner gate location. 1. If the gate location is on a flat surface, the part geometry must include a spherical recess for vestige. 2. If the gate location on an edge, the surface must have a flat recess for vestige. Pin gate or edge gate will leave a mark as shown. Ejector pins will leave marks as shown. In conclusion, this part requires a high degree of precision. Our injection molding machines and manufacturing process are not for precision injection molding. This part requires a secondary manufacturing process, precision CNC machining, and ongoing data collection for concentricity and surface roughness. This part is high risk for scrap and costly quality recalls from the customer plant. Please no quote this project. For your reference, these are the guides for injection molding tolerances. This chart is for straightness or flatness tolerances. This chart is for hole diameter tolerances. Blind hole depth tolerances. Concentricity tolerances. Please note, these tolerances should only be used as guidelines, since actual shrinkage is related to the physical contraction due to cooling, which is in turn greatly affected by the thermal history of the molding. Melt temperature, cooling rate, part thickness, and gate dimensions are all variables which are critical to controlling the amount of shrinkage. Warpage is due to the difference between the mold shrinkage rates in the direction of the mold flow and across the flow. The effect is more noticeable in fiber-filled plastics. The major factor is different wall thickness, as a thick section normally shrinks more than a thinner section. Mold design, gate position, and process control can minimize this effect. However, the basic material behavior cannot be corrected 100%. Therefore, a practical tolerance must be negotiated with the respective production units. The real achievable tolerance is very dependent on your part design. Use these tolerances as baseline criteria and as a guide for manufacturing capability and dimensional accuracy.